We from the team of Step Up Bengal once again welcome all the students preparing for CSIR Math oblique WB set. We are discussing classical mechanics. In today's video lecture, we will ultimately see two problems. Two problems from CSIR Net Math June 2019 and the other one CSIR Net Math December 2018. Both are 3 marks, that means single choice questions. As we have already discussed that these 3 marks questions will be in total 25. 25 into 3, that means total 75 marks is allotted on CSIR for this type of question. And in WB set we have SCQ, single choice question. All the questions are of SCQ type, where we have seen 100 into 2, that means 200 marks on math subject, and each SCQ will carry 2 marks, whereas in CSIR each SCQ will carry 3 marks. So without any further delay, we start the problem. We are discussing how to form Lagrangian. Again, Lagrangian formation is asked. Here we have clearly seen that they have asked about Lagrangian of the system. So L is ultimately, as we all know, T minus B. Now, before starting this problem, let us recall one of our important result, that is the motion of spring mass system. We call it spring mass system, right? So the mass is m and this is string, and this string has elastic constant k. So if we just say this is equilibrium position, that means a string is attached to one end of the mass and the other end of the string is say fixed to a fixed wall. We can say it as some fixed wall. Then if we just draw it further, say up to this position, in the second figure we can easily draw that. Say up to this position we have displaced it. So this is x. X means elongation. That means here the extension. Then we have seen that V equal to half k x square. This is the standard formula for V, that means potential energy. All of you who are new to the channel, please revisit our channel with playlist of classical mechanics, from where you can easily see previous videos and the tips to calculate kinetic energy T and potential energy P. In case of spring mass system, we know the formula is very simple, V equal to half k x square. And T, obviously T in this type of system, this is single variable x, so DOF is 1, so half m x dot square. So ultimately Lagrangian will be of the type half m x dot square minus half k x square, this type. Now come to the question. Suppose a point mass m is attached to one end of a string of spin constant k. The other end of the spring is fixed on a massless cart. Now just draw the figure in brief. If we can draw the figure, say this is some fixed reference this is fixed as this one, and the mass is here, and the mass is attached to a string. The other end of the string is fixed to a cart. একটা গরুর গাড়ির সাথে লাগানো রয়েছে বাকি অংশটা। একটা পাশে আমরা m মাস দেখতে পাচ্ছি। So we have seen one mass m in one end of the string, and the other end of the string is fixed to a cart, and the cart is moving by in horizontal plane by an external device with speed v0. Horizontal plane, in horizontal plane this is moving with speed v0. So if it starts from t equal to 0 time and comes to this position at t equal to t time, obviously this is the distance covered. This distance will be s, say. Now for uniform velocity we know the formula s equal to vt, so ultimately this will be v0t, and the cart is here whose mass is not given. Now what they have given, if the position q of the mass in the stationary system, now as the system, that means cart as a whole, the cart and the mass will form the system. When they move, we just see the movement of this cart in this direction, and also with it the mass is moving. So ultimately the mass, say, finally comes to this point. This is also variable position where its distance is given to be q. Q means Lagrangian coordinate, we have already discussed. This is q. So ultimately the net displacement or elongation, as we have spoken about elongation, that will be q minus v0t, because since there is already s distance covered, so this is to relative to the system. For relative system we all know that if this is q, total distance, and already this is given, then the relative one is just the difference between the two, so q minus v0t. So what will be kinetic energy? Kinetic energy will be half m q dot square minus, what will be potential energy t? T will be half k, here that k is here given spring constant. This is conventional idea, এটা দেয়াই থাকবে। So half k into elongation is q minus v0t whole square. So this will be clearly the answer. Now we have seen within say 2 to 3 minutes we have done this problem. Now take a look at the options, which one is going to be correct. Now take a look. If say someone is not very familiar with the all the details, configuration, etc., yet he or she can easily solve this problem, because in the potential energy in horizontal direction there should be here t minus v format. Potential energy here is always in positive level, that means a positive x-axis. Say positive x-axis is our q, we can consider q as x-axis, q as displacement along x-axis. So this is very similar to this figure 1 system. Okay, so ultimately kinetic energy will be half m x dot square. X dot is very much similar to q dot, so this is clear, but in the all the problems this is given, so there is no need to bother about kinetic energy. Only the potential one is different in each case. So if this t is positive, this v, then we should have minus sign before it for this t minus v configuration of L. So where the plus signs are there, those will be eliminated, and we have only these two options. But see the beauty, v will be always half k x square type, half k x square type, half into spring constant into elongation square. Now, is there any square term in the first option? No. So that will be also eliminated. So this is our answer, which we have done extensively by this figure and this calculation. This will be the ultimately L. L equal to half mq dot square minus half k something. So obviously its answer will be 2. Option 2 is correct. Other options will be eliminated. But for the sake of simplicity, we have discussed what is S, how it does become V0t. Remember one thing, when there is uniform speed V0, this is constant obviously, this is uniform. When we have V, that is not uniform. But if V0 is there or V0, whatever you can say, this is constant, then this is unique. And this is, if this is unique, then the formula to derive distance will always be in the format S equal to V into T type. এই ফরম্যাটে করে নিলে তোমরা এটা বের করে নিতে পারবে। তাহলে নেট হচ্ছে কিউ মাইনাস ভি জিরো টি, আমরা এখানে দেখিয়ে দিয়েছি, সেইটা হয়ে যাবে। কিন্তু এত কিছু কি জানার দরকার ছিল? এখানে তো প্রথমে প্লাস দুটো কেটেই গেল, আর মাইনাসের মধ্যে যে দুটো আছে তার একটা স্কোয়ার নেই। So brief idea L, if we have brief idea about L, that is T minus V, and especially this V, because T in all the cases are same, then we can solve it easily. So this was given in the problem. Now we come to the next problem. This is interesting. Before coming to this problem, we would rather recall again spring mass system. There L is T minus V equal to half m x dot square minus half k x square type. Now mark one of the remarkable achievements in the field of classical mechanics, for especially for Lagrangian mechanics. This is, what is this? This is half mv square type. So kinetic energy is given. This is kinetic energy, this is the type, and here we have potential energy V, potential energy, and kinetic energy is denoted by T. Now if we just say differentiate this L partially with respect to velocity component x dot, then what we have? Then half into m into 2x dot, because the derivative, partial derivative of x dot square will be 2x dot, so 2 will be cancelled. Now take a look at this nice thing, that this becomes m into x dot. So this is of the type mass into velocity. What is this? This is momentum. Now if this momentum is written as mass m into qi, because qi is generalized coordinate, then this momentum will be called generalized momentum. In Newtonian mechanics we have already momentum, but in Lagrangian mechanics, since these qi's are different, we have already discussed. Please revisit for say in lecture 6, 7, 8. These lectures will help you to understand what is generalized coordinates. So the momentum expressed in terms of generalized coordinate will be generalized momentum. How can we achieve that? Look at here. If we have mx dot in our hand, then we must differentiate partially L with respect to x dot. That means we can briefly say it velocity differential of L. If we just differentiate del L by del qi dot, here qi is only one, that is x, so we have differentiated it with respect to x dot. Cannot we call it as velocity differential? Obviously partial velocity differential with velocity differential of L. Now to remember all this, we have just discussed this term. If we take velocity differential of Lagrangian, then we have generalized momentum. Now it may so happen that this qi may be x, then what will be generalized momentum? Del x by del x dot. If this qi is say our r, then that will be del l by del r dot. If this is theta, then that will be del l by del theta dot. If this is phi, then that will be del l by del phi dot. If someone calls it as z, then that will be del l by del z dot, etc. So for generalized all these are generalized, remember this thing, generalized momentum. So to derive the expression for generalized momentum, we just have to differentiate partially the Lagrangian function L with respect to corresponding velocity component. If it is given in x form, then we should take derivative partially with respect to x dot. If it is given to be r, then we just make it r dot and take differential. If it is theta, then we just make it theta dot and take differential, etc. So this is important tricks. This will we have to remember always in exam purpose. Now we should come to the problem, but before discussing that problem, let me just discuss one more thing. That is, if we make take the partial derivative of del L divided by say uh, with respect to del q2. Say we have generalized coordinate, three coordinates q1, q2, q3, as in spherical coordinate system, that may be r, theta, phi, etc. Now say this one is q2 theta. So if we just take differential of del L by del theta and this quantity becomes 0, then this theta is called ignorable coordinate. Remember this term very well. Ignorable coordinate. That means a coordinates, if we take just the derivative with of Lagrangian L with respect to that coordinate, then that must be 0. Clear? So if r is ignorable coordinate, what will happen? Del L by del r will be 0. Whatever may be L, it will be always 0. If phi is ignorable coordinate, then del L by del phi should be 0. Another name is given to this coordinate. Someone call it cyclic coordinate. This is another nomenclature we have to be careful about, because in exam we may not see ignorable, we may see cyclic, or in some other exam we may not see cyclic, may see ignorable. These two are equal. So if some coordinate is ignorable or cyclic, then the partial derivative of Lagrangian function L with respect to that coordinate must be 0. This is important again. Clear? And the important next portion is that when theta or phi or r, whatever it may be, that is ignorable, this is a result all of you should remember well to tackle all the problems in the exam. That result tells us if theta is cyclic, then p theta, that means momentum with respect to that cyclic coordinate, will be always del L by del theta. As we have already seen, generalized momentum due to theta will be just the velocity differential of del L with respect to that theta dot, and that will be constant. That means p theta will be preserved. This is important result. I am telling you once again. If theta is cyclic coordinate, then p theta will be constant. So if phi is cyclic coordinate, then p phi will be constant. That means that will be preserved. In many questions, many exams, we see this type of direct results. Say in some exam, they are given to us that r is ignorable coordinate. Then what is the conclusion? The only conclusion is PR will be constant. This is important conclusion. And the first one, but not the least one, is obviously del L by del R will be 0. So these will be extremely important to tackle the problem given to us. We will see now that how we can tackle that problem. This is the problem. Consider the two-dimensional motion of mass m attached to one end of a spring whose other end is fixed and k be the spring constant. We have already discussed all this in previous problem. That means the first problem of today. The kinetic energy T and the potential energy V of the system is given in this form. T is this one and V is this one. So just let me write those two expressions. What they have given, L equal to half m r dot square plus r theta dot whole square, V equal to half k r square. Then cannot we just derive the expression of Lagrangian by using, this is k, this is t, sorry, L by t minus v. Then what is t? Half into m into r dot square plus r square theta dot square minus v half k r square. Again that format, half k into elongation square, this type. This is our Lagrangian. It is clear that the Lagrangian is given. So we have been asked to solve the problem on where R is dr dt. These are obviously very well known results. R is dr dt theta dot theta dt with respect to time. These are obvious. Then which of the following statement is correct? First of all, R is an ignorable coordinate. Now we have just seen that if R is an ignorable coordinate, then del L by del R should be and must be 0. So first we all differentiate L with respect to R partially, del L by del R. So del L by del R, here there is no function of R except this one. So only we have half into m into the derivative of R with respect to R will be 2R into theta dot square will be there, because this portion will be 0. This R dot, when we take differential, partial differential with respect to R, then this portion will be 0 and this is the answer obviously. And now the second one is this half into k into 2r. So this 2 will be cancelled, this is also cancelled. Now cannot we call it 0 always? No. In general it is not equal to 0. In general this is not equal to 0. So the first option is obviously false. R is not an ignorable, R is not an, they have given that R is an ignorable coordinate, but it is not. Theta is not an ignorable coordinate, second option. So we again take differential with respect to theta and see what happens. Del L by del theta. Here theta is not here in the first expression of kinetic energy. So this will be 0. Again theta is not here also. So that will be 0. So this is 0. That means theta is ignorable or cyclic, whatever you can say. Ignorable coordinate. But have they given it that theta is ignorable? They have given it theta is not an ignorable, so it is also false. Now the two options are there. R square theta dot remains constant, R theta dot remains constant. Now I have already discussed, whenever there is the mention of ignorable coordinates, just think of preservation. Which quantity will be preserved? That will be defined, or rather expressed, when we can just mark what is cyclic. If theta is cyclic, then p theta will be conserved, and from the p expression of p theta can easily derivable from this one, and this conservation, preservation or conservation will give us the answer. So take a look at this beautiful thing that if theta is cyclic or say phi or say r, then pr or p theta or p phi will be constant, and from that constant we can easily tackle this type of problems where some constant word is given. This word is important word. So here what is cyclic coordinate? Theta. Ignorable is theta. So p theta, that means how can we derive that? Del L by del theta dot operation. So what will be that? From here we can just differentiate this, because here we have not any theta dot, so only theta dot is here. So half into m into 2 into r theta dot into r into r square. That means we have 2r, so r square will be there. This will be the expression, that will be constant. Now these two will be eliminated. Now what we have? M r square theta dot equal to constant, implies r square theta dot equal to constant, because mass of a particle is given and that is constant. Say for any system, mass is something that is denoted as m, which is obviously constant except the chapter of varying mass, but here there is no mentioning about these facts. So mass in general constant, so r square theta that will be preserved and that is constant. Now is this given in the last two options? R square theta dot remains constant throughout motion, and the other option is r theta dot. So obviously r square theta dot, this is the answer, this is not. So and option 3 is correct. Now we have already done the problem, this one. Now to see as some coordinate ignorable, we often use an important shortcut clue to see whether a coordinate is ignorable or not. Before ending, I am mentioning, or rather telling you, that secret. If some coordinate, say what is here ignorable? Theta. So to know that, we have to just differentiate L with respect to that coordinate and see whether it is 0 or not. But without differentiating, we can easily say whether a coordinate is ignorable or not. Say how? You can say, how can we say easily that? Take a look at the fact. Here, theta dot means velocity type result, angular velocity. So velocity is here, but is there in the kinetic energy portion theta dot type, or here also? So velocity is here, but this one is not. Take a look at the fact. R is here and r dot is here. That means velocity is here when we consider r as coordinate, but and also r is here. So r dot r here. So there is a bracket. R dot, if r dot is here, r should be there. If theta dot is there, theta should be there. If this happens, then that coordinate can never be cyclic or ignorable. But if theta dot is observable but theta is not, then that will be ignorable. Here r dot r bracket is clearly seen. Yes, is that, আমরা কি দেখতে পাই যে এটা দেখতে পাচ্ছি আমরা? হ্যাঁ, দেখতে পাচ্ছি। তাহলে যখনই আর ডট এবং করসপন্ডিং আর দুটোই দেওয়া আছে, সে ইগনোরেবল হতে পারে না। যখন আমরা দেখব ভেলোসিটি কম্পোনেন্ট ইজ গিভেন বাট দ্য করসপন্ডিং কোঅর্ডিনেট ইজ নট, দেন দ্যাট coordinate will be ignorable. So before finishing, let us write down that result. A coordinate, obviously generalized, because in Lagrangian system we have only generalized coordinate, is ignorable. This is only shortcut clue, not written in the books often, but people from physics background often uses it. Ignorable, a coordinate is ignorable if velocity component, say this coordinate is theta. Velocity component means theta dot is seen. It is clearly seen, but theta is not seen. What is theta? Simple coordinate. Velocity component is seen. This coordinate is in general displacement. Here it is angular displacement. So theta is not seen. Then that coordinate will be ignorable. Remember this important shortcut clue that will help tremendously in the exam hall. That this will give you the chance that without differentiating L, you can easily arrive at the result. So until we just upload new videos, please like, comment and share with those who are really interested in higher maths or in any kind of competitive exam. So until then, goodbye.